Welcome. My name is Carlos Molina Holguin, and in collaboration with Jorge Macías and Armando Gallegos, we would like to present you our work on numerical solutions and conservation analysis of the fractional Davey-Stewartson system for the International Conference Computational and Mathematical Methods in Science and Engineering 2025. Firstly, I would like to outline my talk. We will have a brief introduction on our system of equations. We will discuss the mathematical model of the fractional generalized Davey-Stewartson system. We will pass through our numerical method, which is using Crank-Nicolson scheme. We will talk about the conservation of the main properties, which are mass, energy, and momentum. And we will show our numerical simulation, discuss about results, conclusions, and future work. The Davey-Stewartson system models the interaction of short-wave packets with mean flows in dispersive media, such as shallow water or nonlinear optics. Its fractional generalization replaces integer Laplacians with Riesz fractional derivatives to capture non-local dispersion effects, allowing us to study anomalous wave propagation and long-range interactions in an unified framework. So this system of equations looks as follows. This is the fractional generalized Davey-Stewartson system. As we can see, it is a tree system of equations which presents non-linearities, which is the reason why this system is difficult to analyze analytically, and numerical tools come handy for this kind of equations. For these equations, we have the following dependent variables. We have u, which is the complex valued transverse shortwave mode, w, real longitudinal mode along x, which is the mean flow, and v, real longitudinal mode along y, orthogonal to w. This system of equation, as we can see, has some parameters. We are going to talk about it in the next slide. These are our physical parameters which describe the behavior of this system of equations. The first coefficients are the dispersive coefficients, alpha and beta, for u in x and y directions. Then we have a non-linearity strength, self-focusing or defocusing term. We have a coupling constant between u and mean fields, w and v. Dispersion coefficients for w and v in x and y directions, and a cross-coupling strength between w and v. All of these parameters determine the physical behavior of the system that we are analyzing. And we have also the fractional order of derivation, which are tied to the nature of the fractional calculus. For our work, it is very important to analyze the conservation of mass, energy, and momentum, which are the invariants. So in our previous work, we presented that it was possible to show the conservation of these properties, but now we would like to show that also on a discrete scheme, it is also possible to show the preservation of these invariants. So we are going to analyze the conservation of mass, energy, and momentum in the following section, which is our numerical method. Before showing the conservation, I would like to talk first of how our numerical method is built up. First, we have a spatial and temporal grid. It is important to have a discretization for both space and time in order to have this numerical method working. For the temporal discretization, we are using Crank-Nicolson, which allows us to have second order of accuracy due to its implicit nature. For stability purposes, we will also have this relaxation for all our variables, relaxation for u, w, and v. For the fractional derivatives, we are using centered fractional differences by using Ortigata weights that are described by the gamma function, and then using second order approximation of the Riesz derivatives all along this scheme. Using all these tools, we are able to discretize the fractional generalized Davey-Stewartson equations, and they will look like as follows. So this is the system that we are going to be analyzing, and for this first part we are going to be using the following initial conditions. Initial values for u, w, and v, and boundary conditions, homogeneous Dirichlet conditions on all borders. So now let's go and talk about the conservation of these properties. To demonstrate the conservation of the mass, we, as said before, we are using Crank-Nicolson, time-stepping, and Ortigata discretization. And we will take the first equation of our system and multiply it by the following term. And then we will take the inner product. Using skew adjointness of fractional operators and symmetry in time averaging, we will come to the following result, which shows us that the mass is preserved over time for the discrete regime. Now, for the conservation of energy, we are using the following expression, and we will also take the first equation of the fractional discretized generalized Davey-Stewartson system and multiply it by the following term. Then we will take the real part of that remaining equation, use some identities for the real inner product, and have the same relation for y components and nonlinear terms. Combine this equation with the time differentiated elliptic equation for w and b. After some algebra, all these terms will be cancelled out, and we will have our preservation of their energy over time. For the discrete momentum on x and y directions, it is also the same procedure. If we demonstrate one of them, we are going to get the same result for the other one. So we take again the first equation, multiply it by the following term, and also its complex conjugate. Use also identities for the inner product, derive the evolution for the momentum, and then after some algebra we will also came to the same result. Momentum is preserved over time. So in this case also all cross terms and mixed derivatives are cancelled out due to symmetry. And all of these results are very important because we are showing that using fractional calculus and also on a discrete scheme, we are having preservation of the invariants, which complies to the physical meaning provided by these equations. So now that we have proven that the invariants are preserved over time, we can get started with the numerical simulation. For our simulation, we have the following setup. For our domain size, we have symmetry on x and y axis, grid resolution 200, and our time step should be small, 1 times 10 minus 4. This is because we wanted to have stability and accuracy in our results, and also we are testing our system at time 0.5. For the initial conditions, we decided to have a soliton propagation, so we have soliton initial conditions, which are given by the following formulas. And again, our boundary conditions are homogeneous Dirichlet on all borders. Now, talking about our numerical scheme, we have a discretization for space, Riesz fractional derivatives using Ortigueira convolution. For the time, we have Crank-Nicolson using circle order and semi-implicit scheme. For the non-linear terms, we solve them using Picard iteration at each time step. And for the elliptic coupling solver, which were the terms for W and B, we use Poisson with the Dirichlet boundary conditions, and we use finite difference Laplacian, which gave us the following matrix, which was ensemble ones. And thanks to MATLAB, we have solvers that help us with sparse systems, which gave us the possibility to solve big matrices. And using all this configuration, we were able to enforce the boundary conditions that we were waiting for. Now we can see the results under that configuration. For our presentation, we have three different configurations. One, testing the classical limit using the derivative orders of 2 in our fractional system. We recover the standard Davey-Stewartson system. We tested also a moderate fractionality. All our derivatives were set up at 1.5, which is half Laplacian benchmark from the literature. And then we also wanted to test strong fractionality using 1.2, which would pronounce non-local tile effects. We had the following fixed parameters for our model, and then we can see the results. For the classical limit, we have here the graphics, the figures for the norm of U, W, and B at time 0.5 using the classical limit. So here we can see the behavior of this soliton propagating over a medium. Which is important for us is the following: the preservation of the quantities. And here we can see that also mass, energy, and momentum are preserved over the time of our simulation. We can see small deviations, but those could be originated by numerical fluxes or the spatial and time discretization that we could be refining. But in general terms, the properties are preserved, and we can see preservation in the order of times 10 minus 3. For the moderate fractionality, we have also the norm of U, W, and B, and we can see also smooth behaviors also on the borders where we place the boundary conditions, the Dirichlet, and also conservation of the invariants. Mass, energy, and momentum remain also constant or present small deviations, but in general terms, they also remain constant. And for the last case, for the strong fractionality, we can see here also a smooth behavior on the borders and the representation of the soliton and its components. But what we wanted to see was the conservation of the invariants, and here we can see also same results. So with these results, we can say that working with fractional calculus, we are also able to preserve these invariants, and then introducing a numerical method, we are also not worried about losing these properties, which give us fidelity to the physical results that we want to approximate using these numerical methods. For conclusions, so we implemented Crank-Nicolson solver with Picard iteration for the fractional generalized Davey-Stewartson system. The numerical experiments demonstrated that the conservation of mass, energy, and momentum was possible, and the range of the errors or deviation of the results were minor to 10 times minus 3. Finite difference Dirichlet boundaries enforce W and B to be 0 exactly at the border, and this eliminates order artifacts that ensures consistency with non-local operators. Here it is important to mention that after using finite differences, we were trying to use spectral methods. And when we were using spectral methods, we were having troubles to have our Dirichlet boundary conditions. They were not respected. So we changed our scheme, and we were able to have these results that you are seeing today. For future work, we would like to also continue working with spectral solvers, and for that we would like to investigate absorbing damping boundary layers, PML sponge layers, to suppress the residual reflection due to the nature of the fractional derivatives and also the spectral methods. Develop adaptive time-stepping schemes based on error controls using Picard residuals and CFL current Friedrich-Levy condition in order to control the error. Extend to more general domains, not just non-rectangular domains with also different coefficients, and have also higher spatial discretizations. And then also compare the results obtained with fractional calculus, compare it to classical dynamics, and also compare it to reported solutions for other similar systems. With this, I conclude my presentation. I would like to thank you for your attention, and if you have questions, please do not hesitate to contact us. These are the references that we use for work. Thank you again for your time.